Chapter 10. Electricity and Electronic Engine Controls. After studying this chapter, you should be able to explain electricity in terms of electrons and what makes electrons move. Define voltage, current, and resistance and explain how they are related. Explain the basic operation of diodes and transistors. Describe RAM, ROM, and PROM and explain what they do. Explain how the ECM controls engine operation. The electric ignition system supplies the sparks that ignite the compressed air fuel mixture in the engine cylinders. Chapter 9.9. This makes the engine run and produce power to move the car. To get the engine running, the electric starting motor must crank the engine until it starts. The battery supplies the power for cranking. The engine also has electronic controls that time the sparks so they get to the spark plugs at the right instant. This is just before the pistons reach top, dead center, TDC, on their compression strokes, some figure 9.7. On most engines, the electronic controls also time the opening of the fuel injectors. In Chapter 19, they open at the proper time to allow the fuel and air to mix as it enters the engine cylinders. The electronic controls determine how much fuel to deliver. The engine needs more fuel. If the driver is depressing the accelerator, pedal for acceleration and higher speed. The following sections describe electricity, magnetism, electronic, and electronic engine controls. An understanding of these subjects, as explained here and in later chapters, helps you understand engine operation. Also, many times you will need this background to successfully diagnose and correct various engine and electrical troubles. Chapter 10.2. Electricity and electric current. Electric current is a flow of electrons. Just like water flows in a pipe, electrons flow in a wire. The electrons come from atoms. Figure 10.1. Everything in the world is made of atoms. In Chapter 9.1, there are about 100 different kinds of atoms. Atoms of one kind grouped together are called an element. The atoms of certain elements join together in chemical reactions such as combustion. Chapter 9.2. One basic difference among the atoms is the number of electrons that circle the center, or nucleus of the atom. Figure 10.1. For example, an atom of the gas hydrogen has only one electron circling its nucleus. The copper atom has 29 electrons circling its nucleus. Atoms are very small. Electrons are even smaller. It takes 100,000 billion, 100,000 electrons side by side to measure a single inch. Chapter 10.3. Electrical charges. Electrons carry a negative charge, written minus or G. The nucleus of an atom has a positive charge, written plus or plus. The electrons circle or orbit the nucleus. They are held in their orbits by the attraction between opposite electrical charges. Figure 10.2 shows how unlike electrical charges attract and like electrical charges repel. In the automotive electrical system, Figure 10.3, the battery and the alternator supply electrons. Electrical current. They mass electrons at their negative, minus, or terminal. They take electrons away from their positive, plus, or plus terminal. Connecting a wire from one terminal to the other completes the electric circuit. The electrons flow through the wire. Figure 10.4. This is caused by the repelling force among the electrons at the negative terminal and the attracting force at the positive terminal. It has a shortage of electrons. This difference of potential causes electrons to flow from the negative terminal to the positive terminal. The flow of electrons is an electric current. It will power a light bulb or other electrical device connected in the circuit. Figure 10.4. Chapter 10.4. Measuring electricity. Electricity is measured in two ways. 1. By the amount of current, electrodes flowing. This measurement is in amperes or amperage. 2. By the electrical pressure, difference of potential, between 2 points that makes the electrons move. This measurement is in volts or voltage. Amperage is measured by an ammeter. Voltage is measured by a voltmeter. Figure 10.5 shows an ammeter and a voltmeter connected into a circuit. The ammeter is connected into the circuit to measure the current amperage flowing. The voltmeter is connected across the circuit. It measures the electrical pressure, voltage, that is forcing the current to flow. Current flowing through a wire creates a magnetic field around the wire. The strength of the Magnetic field increases or decreases with the amount of current flowing. To avoid breaking the circuit to connect an ammeter, an inductive ammeter is used. Figure 10.6. It has an inductive pickup that clamps around the wire. The pickup senses the strength of the magnetic field. Using this information, the digital multimeter can then display the amount of current flowing. Note: a multimeter, or multitester, is often used to make electrical measurements. In effect, the multimeter is two or more test instruments combined in a single case. A meter with a pointer or needle is an analog meter. A digital meter, figure 10.6, displays numbers. Chapter 10.5. Conductors and insulators. Conductors allow current to flow. Insulators prevent current from flowing. In the electrical system, conductors carry, conduct, current to devices that run on electric current. There are various sizes of conductors, usually covered with insulation. Figure 10.7. The conductors are wires of copper or similar metal twisted together to make cables. A cable is more flexible than a single wire of the same size. The insulation covering the cables prevents the current from flowing in the wrong direction. If the insulation fails, current could take a shortcut through the metal of the car body or frame. This is a short circuit. It can cause trouble and damage. Chapter 27.11. Chapter 10.6. Conductor resistance. Conductors, wires and cables offer very little resistance to the flow of electric or current through them. The amount of resistance depends on the diameter, size of the cable, figure 10.8, and the length of the cable. Resistance is measured in ohms. The symbol for ohms is S. For example, number 10 gauge cable is about 100 inch. 254 mm in diameter, figure 10.8. 1,000 foot, 305 ohm length of this cable has a resistance of 1 ohm. A 2,000 foot or 610 length has a resistance of 2 ohms. With twice the length, there is twice the resistance. If the cable is heavier, larger in diameter, it has less resistance. A number 4 gauge cable, figure 10d8, is 0.200 inch mm in diameter. 1,000 foot length of this cable has a resistance of only 1/4 ohm. The longer the cable, the farther the electrons, current, have to travel. This means a higher resistance to the current flow. However, the larger the cable diameter, the larger the path in which the electrons move. Its resistance to current flow is lower. Chapter 10.7. Temperature effect. With most materials, such as copper, the resistance goes up as its temperature increases. The size of the cables used in automotive electrical circuits is large enough to carry the required current without overheating. The starting cable, figure 10.6, carries the high current needed to operate the starting motor. This cable is much larger than the ignition cable, which carries only a small current. Compare the size of these cables in figure 10.7. The heating effect is used to advantage in most light bulbs. They have a coil of tungsten wire called a filament, fig 10.5. When current flows through the filament, it gets so hot that it glows and gives off light. A few materials have an opposite effect. Their resistance decreases as they get hot. For example, the sensor or sensing unit. Chapter 25-19. In the engine for the coolant temperature, indicator loses resistance as its temperature increases. It then passes more current to a gauge or light in the instrument panel, which alerts the driver to engine overheating. This type of sensor is a thermistor. Note: a sensor is a device that receives and reacts to a signal such as a change in temperature, pressure, or voltage. A variety of sensors is used in the automobile. Chapter 10-8. Ohm's law. Ohm's law relates the current, voltage, and resistance in a circuit. The law says that current flow is directly proportional to the voltage and inversely proportional to the resistance. This means that if pressure, voltage increases, more current, electrons, will flow. If resistance, ohms, increases, less current will flow. This is shown in the formula, where is current in amperes, E is electromotive force, voltage, in volts, R is resistance. In ohms, a common cause of electrical trouble is excessive resistance. Not enough current flows. This may be due to loose or corroded connections, broken wires in the cable, or a defective switch. Chapter 10 to 9 One-Wire System. The electrons must have a complete circuit through which to flow. Figure 10 to 5. They leave the negative terminal, go through the circuit and electrical device, and return to the positive terminal. The return path is ground. It is shown in wiring diagrams as for H. To reduce the amount of wiring in the vehicle, the metal engine, chassis, and body parts serve as the reader circuit. Figure 10.9. This is a one-wire or ground return system. Only one wire or cable connects to the electrical device. Attaching the case of the device to a grounded part of the car completes the circuit. This is a case ground. It is used in starting motors. Figure 10 to 6 and other automotive electrical equipment. Most automotive electrical circuits can be divided into two parts for diagnosis and testing. These are the insulated circuit and the ground circuit. The insulated circuit is from the battery positive terminal to the light or electrical device. Figure 10 sign. The ground circuit is from the light or device back to the battery negative terminal. Chapter 10.10 Magnetism. Two types of permanent magnets are bar magnets and horseshoe magnets. See Figure 10.10. Magnets have poles, N for north and S for south. Unlike poles attract. Figure 10.11. North attracts south. South attracts north. However, like poles repel each other. Figure 10 to 12. North repels north. South repels south. These actions between magnetic poles make many electrical devices work. For example, the starting motor develops high torque, twisting force, so it can crank and start the engine. This torque comes from the attraction between unlike magnetic poles and the repulsion between like magnetic poles. Chapter 10 to 11 Electromagnetism. Most permanent magnets are not strong enough to repel and attract with sufficient force to crank the engine. The magnetism must be greatly strengthened by an electric current, flow of electrons. Electrons have charges of negative electricity, which carry a very small magnetic field with them. A single electron has too little magnetism to be noticeable. However, when billions of electrons start flowing in an electric circuit, their magnetism adds up. This effect is electromagnetism, a coil of wire wound on a tube, Figure 10.13, and connected to a battery, becomes a magnet, an electromagnet. One end of the coil becomes a north pole, the other end a south pole. The poles can be reversed by reversing the connections to the battery, sending the current through the coil. In the opposite direction reverses the magnetism. All these actions are used in the motors, alternators, relays, and solenoids in the automobile. For example, the Ohm solenoid is a coil of wire with a hollow center. Figure 10.14. When connected to a battery, the solenoid coil produces a magnetic field. The iron core is pulled into the solenoid by the magnetic field. See Figure 10.14a. However, if the iron core is magnetized as shown in Figure 10.14b, the similar poles, S to S, oppose each other. Then the magnet is pushed out of the solenoid coil. Chapter 10.12 Introduction to Electronics. Electronic means of or pertaining to electrons or electronics. This includes any device operated by electrons. It also includes semiconductor devices such as diodes and transistors. Electronic systems follow the rules of electricity. Wires must connect the various parts into complete circuits and voltage must be available. However, there is a difference. Electrical systems primarily use electric power to produce heat, light, or motion. Electronic systems usually include an electronic control module, ECM, with much greater capability. Chapter 10 to 16. It may receive signals, process them, make decisions, and then send commands that control other devices. Chapter 10 to 13. Semiconductors. Materials through which electrons, current, can flow are conductors. Chapter 10 to 5. Insulators are materials through which electrons, current, cannot flow. There is a third kind of material called a semiconductor. Under some conditions, it can be either a conductor or an insulator. Semiconductors are used to make solid-state devices. They are called solid-state because they are solid and have no moving parts except electrons. Chapter 10.14. Diode. The diode is a widely used semiconductor device. It acts as a one-way check valve for electricity. For example, the alternator in the electrical system, figure 10.3, produces electrical current. However, this current is alternating current, AC. It alternates, or flows first in one direction and then in the other. The automotive electrical system cannot use AC. It must have direct current, DC. The diode rectifies or changes the AC to DC, figure 10.15. When the current from the alternator tries to flow in the wrong direction, the diode stops it. The diode lets the current through only when it flows in the other direction. This is the battery charging direction. Most diodes are combined with other semiconductor devices into an integrated circuit, IC, or computer chip. Chapter 10.16. Chapter 10-15 Transistor. The transistor is a semiconductor used to control the flow of an electric current. A transistor can act as a switch and stop current flow, or it can act as an amplifier. When supplied with a varying small current, the transistor then allows a varying larger current to flow. Like diodes, Chapter 10.14. Transistors can be very small. Figure 10-16 shows how the transistor controls a circuit when the switch to the transistor is closed. Figure 10.16a. A 0.35 ampere flows to the transistor base. This turns the transistor into a conductor and allows 4.5 amperes to flow through. When the switch opens, figure 10.16b, no current flows to the transistor base. The transistor then switches off the current that was flowing through it. Chapter 10.16 Electronic Control. Module ECM. Figure 10-17 shows a typical electronic control module, EM. It is also called an electronic control unit, the ECU, microprocessor, computer, controller, and other names. The ECM serves as the processor or decision maker in an electronic control system. The two main parts are the IC, chips that contain the microprocessor, and the memory, 18. The diodes, transistors, and other devices that make up the chips are often too small to be easily seen. Many thousands are put together to form a single chip. These chips are the basic components of electronic controls. Chapter 10.17 Microprocessor. The microprocessor, figure 10.18, is also called the Central Processing Unit, CPU. It is the solid-state device that controls information flow in a computer. A set of instructions, called a program, is designed into the microprocessor to tell it what to do. By following the program, the microprocessor does the calculations and makes the decisions to solve a problem. The problem may be complicated and have many parts. However, the microprocessor solves it quickly, often in thousandths of a second or less. The microprocessor chip is sealed in a protective package or carrier. Figure 10.18. Pins connect the various circuits of the microprocessor to the input and output devices. Chapter 1.19. Their signals are received and sent through connections or terminals in the ECM, wiring harness connector. Figure 10.17. Chapter 10.18 Memory. The microprocessor cannot store information or data. To do its job, the microprocessor needs access to a great variety of information such as specifications and formulas. This information is stored in an electronic storage device called a memory. The memory stores information, data, for recall later. Computers and microprocessors use two types of memory: read-only memory, ROM, and random access memory, RAM. The microprocessor can read the information in a ROM memory, but cannot change it. A programmable read-only memory, or PROM, is a removable memory chip that can be reprogrammed by another program or computer. The microprocessor can read information from the RAM and change or write new information into it. Random access memories may be volatile or non-volatile. A volatile memory stores information temporarily, as long as battery power is available. Disconnecting the battery erases all the stored data. The information stored in a non-volatile memory is not lost by disconnecting the battery. Figure 10-17 shows two types of memory chips in an ECM. The lookup tables contain data about the car or conditions that are permanently stored on the chip. This is a non-volatile memory. Disconnecting the battery does not affect it. The Keep Alive memory, KM, figure 10-17, is a volatile memory. Some of the data stored in it includes trouble codes if a failure occurs in the system. The Keep Alive memory may also make changes in how the vehicle is operating. This is partly based on information from the lookup tables. If the battery is disconnected, all information in the Keep Alive memory is lost. However, nothing is lost from the non-volatile lookup tables. After reconnecting the battery and starting the engine, the COM goes to the lookup tables for the needed information. This enables the Keep Alive memory to re-layer all the information that was stored in it previously. As long as the battery is connected, a small current flows from the battery to the Keep Alive memory. This is called Key-Off Current Drain. Chapter 30:16. It may eventually discharge the battery unless the engine is started and the battery is charged. Electronic Engine Controls. Chapter 10:19. Controlling the engine. Most engine systems and devices require some type of management or regulation. Otherwise, an out-of-control condition may exist. This could damage the vehicle or engine, especially if the driver fails to correct or control the condition. Some engine controls are mechanical. An example is the gas pedal or accelerator pedal. As the driver pushes the pedal down, linkage to the engine opens the throttle valve. This allows more air-fuel mixture to flow into the engine cylinders, increasing engine speed and power output. When the driver relaxes the accelerator pedal, the throttle valve partly closes. Less air-fuel mixture enters the engine, so it produces less power. Other engine controls are electromechanical. They provide mechanical action when fed an electric current. An example is the solenoid. Chapter 10:11. Chapter 10-20. Electronic Engine Controls. The basic parts of a control system. Chapter 119 are the inputs, the control unit or decision maker, and the outputs. The input devices are sensors. The output actuators. In the car, the decision maker or controller may be one of three types. 1. The driver of the car. 2. A mechanical governor. 3. An electronic microprocessor. Most automotive vehicles have an electronic engine control EEC system. 1012. It usually controls the fuel and ignition systems. The figure 1019. This allows the engine to operate as fuel efficient as possible. Engine exhaust emissions are minimized, while the engine can still produce maximum power if necessary. Many other components and systems in the car may be controlled by the engine ECM or by a separate microprocessor or computer. These include most components that operate under varying conditions, such as the charging system, transmission or transaxle, suspension, brakes, air conditioning, and driver information systems. Later chapters describe these components and systems. Multiple choice test. Select the one correct, best, or most probable answer to each question. You can find the answers in the section indicated at the end of each question. 1. Electrons flowing in the same direction are called. Chapter 10:2. A. A nucleus. B. Magnetism. C. Voltage. D. Electric current. 2. Voltage is. Chapter 10:4. A. Current flow. B. Resistance to current flow. C. Electrical pressure. D. Amperes flow. 3. All of the following are true about resistance in a cable, except Chapter 10-6 and 10-7. A. Resistance decreases with increasing temperature. B. Resistance decreases with larger diameter. C. Resistance increases with increasing length. D. Resistance increases with increasing temperature. 4. Technician. A says, according to Ohm's law, more current will flow if the voltage increases. Technician B says more current will flow if resistance increases. Who is right? Sun Chapter 10:8. A. A only. B. B only. E. Both A and B. D. Neither A nor B. 5. All of the following are true about the ground return system except Chapter 10:9. A. Uses the metal engine, chassis, and body parts as the return circuit. B. Uses 2 insulated wires to each electrical device. C. Uses 1 wire and a case ground. D. Uses electrons that leave the negative terminal. 6. Technician A says a solenoid with a magnet core is a pull-in solenoid. Technician B says a solenoid with an iron core is a push-out solenoid. Who is right? Chapter 10:11. A. A only. B. B only. C. Both A and B. D. Neither A nor B. 7. Technician A says, the diode is a one-way check valve for electric current. Technician B says the diode changes AC to DC. Who is right? The chapter 10:14. A. A only. B. B only. E. Both A and B. D. Neither A nor B. 8. The solid-state device that can act as a switch or an amplifier is A. Chapter 10:15. A. Diode. B. Transistor. C. Conductor. D. Resistor. 9. All of the following are true about the microprocessor, except Chapter 10-17. A. Controls information flow. B. Follows the instructions in its program. C. Performs calculations and makes decisions to quickly solve a problem. E. Permanently stores large amounts of data in its memory. 10. The small electric current that flows, with the ignition key off, from the battery to a volatile memory. Chapter 10:18. A. Is called key-off current drain. B. Is also needed by the non-volatile memory. C. Will discharge the battery overnight. D. Will always set a trouble code. Review questions. 1. Describe how an inductive ammeter measures current flow. Set Chapter 10:4. 2. Explain the advantages of using a case ground. Chapter 10:9. 3. What makes solid-state devices solid-state? Chapter 10:13. 4. Describe the construction of a computer chip and the two main types of chips in the ECM. Chapter 10:16 to 10:18. 5. List the three parts of a control system. Describe the job the EEC system performs in controlling engine operation. Chapter 10:20.